Welcome back. Today, we're jumping right into an explainer of a captivating cosmic mystery that perfectly mirrors what our very own Milky Way might look like from the outside. We are focusing all our attention on Caldwell 23, the Outer Limits galaxy. It's a stunning celestial object that astronomers have affectionately, and honestly quite appropriately, linked to that classic sci-fi moniker.
To really set the stage for today's journey, we have to turn to the classic 1963 television intro that brilliantly captures the sheer awe of stepping into the great unknown. You know the one. There was nothing wrong with your television set. You're about to experience the awe and mystery which reaches from the inner mind to the outer limits. It's just incredibly fitting, because when we point our most advanced telescopes at this particular galaxy, we are quite literally stepping past the boundaries of our own galactic neighborhood to observe mechanisms that are otherwise completely hidden from us.
30 million. That enormous number is the distance in light years to Caldwell 23, which is also known in the astronomical catalogs as NGC 891. Located deep within the Andromeda constellation, the spiral galaxy is suspended in space at a distance that makes it far enough to see in its entirety, yet close enough for our modern observatories to resolve its incredibly intricate, dusty details. Section 1. Our edge-on cosmic twin. So, the real value of Caldwell 23 isn't just that it's another spiral galaxy, it's the highly fortuitous angle at which it sits relative to Earth. Captured by the Subaru telescope's FOCA-S instrument, we can see its nearly perfect edge-on orientation. It's inclined at roughly 89.7 degrees, making it an absolute goldmine for astronomers. Inside the Milky Way, gas and dust constantly block our view of our own galaxy's overall structure. But here we can cleanly separate the main stellar disk from the outer halo, giving us this beautiful, unobstructed cross-section of a galaxy's anatomy.
And when you dig into the data, you see just how similar its vital statistics are to the Milky Way. It really is our very own cosmic twin. It shares the exact same Hubble classification, meaning it's an unbarred spiral galaxy just like ours. It rotates at roughly 225 kilometers per second, and its star formation rate sits right between 3.8 and 5.0 solar masses per year. In luminosity, in size, in activity, looking at Caldwell 23 is essentially looking into a 30-million-year-old mirror.
Section 2. Beyond the visible light. But to truly understand the mechanics of this twin galaxy, we have to look past the visible spectrum. Why? Because galaxies aren't just flat, static disks of stars as they usually appear to our human eyes. They are actually surrounded by a massive, invisible halo known as the circumgalactic medium, or the CGM. Think of it as a massive extended envelope of diffuse gas, cold dust, and cosmic rays that dynamically interacts with the main galactic disk. It effectively acts as the galaxy's atmosphere and, as we'll see, its recycling center. When we take that visible light structure and compare it to infrared data from the Spitzer Space Telescope, a completely different, much thicker galaxy emerges. This infrared view exposes the thermal heat radiating from cold dust, stretching thousands of parsecs into what we previously thought was just empty space. We are looking at an extended dusty halo, reaching way beyond the thin stellar plane.
And this isn't just a fluke. A massive array of multi-wavelength observations from the Herschel Space Observatory and others conclusively proves that the dust halo extends much further vertically than the stars themselves. Whether we're looking at different wavelengths tracing varying temperatures of cold dust, or even radio continuum data, we see this thick dust component completely enveloping the core. And here's the kicker. It's not just sitting there passively. The temperature gradients and the distribution of this dust actually tell a story of violent ejection.
Section 3. Superbubbles and galactic fountains.
Right, so this extended halo isn't just some stagnant cloud. It is a chaotic, active environment shaped by immense internal forces, where the galaxy literally breathes out its own interstellar material. Think of a superbubble as an explosive cosmic exhaust pipe. When you have regions of elevated star formation, you get massive stars that live fast and die hard in brilliant supernova explosions. And when a bunch of these supernovae go off in the same neighborhood, their combined shockwaves blow a massive cavity of hot gas right out of the interstellar medium. This plays a huge role in physically moving material completely out of Caldwell 23's main disk. It forms a relentless, continuous cycle. Step 1, we have elevated star formation driving these supernova. Step 2, superbubbles form, creating immense, unimaginable pressure. Step 3, interstellar shocks literally entrain dust and gas. And step 4, they shoot it up into the halo like spectacular galactic fountains. This is the disk-halo connection in action, folks. It's blowing material high above the galactic plane before it eventually cools down and rains back onto the disk.
Now, because of this intensely violent process, the dust found up to 2 kiloparsecs above the midplane is actually chemically different from the core. The abundance of small grains relative to large grains in the halo is almost halved compared to the midplane. What does that mean? Well, it strongly suggests that as the dust is forcefully blasted upward by these fountains, the delicate small grains are completely destroyed by the violent interstellar shocks, leaving only the larger, hardier grains to populate the upper halo. Crazy, right?
Section 4. Streams of ghostly stars.
However, internal explosions aren't the only forces violently shaping this outer limits galaxy. Galaxies frequently interact with their neighbors. Herschel's spire maps reveal a really strange dust spur on the eastern side of the galaxy. This filament contains nearly 800,000 solar masses of dust. Let that sink in. That is a colossal amount of material just hanging out in the intergalactic medium, posing a fascinating question. How on Earth did it get there?
Well, the mounting evidence is pretty hard to ignore. From tracing the radial velocities of 125 individual planetary nebulae to measuring the strange lack of neutral hydrogen relative to dust in that spur, it all strongly suggests that Caldwell 23 literally swallowed a smaller satellite galaxy. The planetary nebulae act super weirdly, showing strong rotational asymmetry at high altitudes, meaning they're moving in chaotic, unaligned directions. They're acting like ghostly tracers of a previous minor merging episode. We are actually seeing the incompletely mixed remnants of a dwarf galaxy that just ventured a little too close and was completely torn apart by tidal forces.
Section 5. A living, breathing galaxy. So, what should you really take away from all this? All of this complex data paints a remarkably dynamic picture. Caldwell 23 is far from a static, boring collection of stars. It's a bustling, violent, and recycling ecosystem. By looking 30 million light-years away at this perfect edge-on twin, we are actually decoding the hidden mechanics of our very own galactic home. The galactic fountains, the superbubbles, the shredded satellite galaxies forming extended stellar streams. These are the exact processes assembling and shaping the Milky Way right now, completely obscured from our terrestrial vantage point.
Which leaves us with this final, awe-inspiring thought to ponder about our own mysterious place in the universe. If distant observers 30 million light-years away in the Andromeda constellation were to turn their telescopes towards the Milky Way right now, do they see the outer limits? Keep looking up, keep asking questions, and I'll see you in the next explainer.